Few last words to say about wood stoves before going on to water, steam, and ice. I hope that you have a pretty good sense of conduction and convection as mechanisms for transferring heat from hot objects to cold objects. Any questions about conduction, convection? The one I want to make sure I've dotted all the I's and crossed the T's on is thermal radiation, which again is the transmission of heat by way of electromagnetic waves, which include visible light, infrared light, all of the relatives of light, which include radio waves, microwaves, and stuff. When an object, so the pieces that I want to make sure are clear, when an object is really hot, like the temperature of the sun, the spectrum of its thermal radiation includes a great deal of visible light. Basically, the hotter the object is, the faster its little particles are jiggling back and forth with thermal motion, the higher the frequencies of the electromagnetic waves they emit, and with higher frequency you get shorter wavelength. Those go hand in hand for light. So for very hot objects like the surface of the sun, the thermal motion is so fast that the electromagnetic waves that are emitted by these particles include a lot of visible light, so you can see the stuff. And because most of the thermal radiation from the sun is in the visible, you have a pretty good sense whether something is black or white or something in between for visible light. A surface that looks white, like this sheet of paper, it's white in the visible. You could tell that. You look at it, you see most of the light that hits it from visible sources reflects back. If this sheet of paper didn't burn, if it could stay solid and so on, and you heated it to the temperature of the sun, it would not glow brightly. It would be capable of emitting the same spectrum of light as the sun, but because it's white rather than black like the sun is, it doesn't glow. It won't glow well because white is terrible at both absorbing and emitting. It's absorbing light and emitting its own thermal radiation. So you know that white objects in the visible, when heated to the temperature where they would emit visible thermal radiation, they won't do a good job of it. Is that okay? Where things get mysterious, I should just finish it off. If this were a black sheet of paper, if I colored it all in black with a magic marker, then it would suddenly become very good at emitting thermal radiation in the visible. So easy to see. It's in the infrared that life is tricky. All of us are emitting, and everything in this room, with maybe, nothing's very hot in this room at this point. Not sun hot, or even close. And consequently, everything in this room is emitting thermal radiation in the infrared, which is deceptive. You can't judge the color of something by looking at it with visible light. You can't be sure what it looks like in the infrared. There are instruments that can see what things look like in the infrared, but it's not us. And it turns out that virtually everything made of organic material, so all the wood, paint, plastics, all these things that are us, made of sort of ordinary organic molecules, and many other molecules, they're very dark in the infrared. In the part of the infrared associated with room temperature thermal radiation, they're all virtually black. So everything in this room is very good at absorbing room temperature thermal radiation and emitting room temperature thermal radiation, including us. The exception to this is things that are electrically conducting. So when I talked about shiny, and I may have misled you into thinking, it's not that they're flat as opposed to rough. It's that things that conduct electricity are very good at reflecting electromagnetic waves. The electromagnetic waves go into the thing that conducts electricity. They cause electric charges to begin sloshing back and forth in those surfaces, the surface of the electrical conductor, and that motion of charge in the conductor absorbs the incoming wave and re-emits it, often at a mirror angle, so that they act as mirrors for electromagnetic waves. This is why when you look at an ordinary bathroom mirror, you see a reflection of yourself. It's that metal coating on the back of the glass. It used to be silver. Now, these days, it's almost entirely aluminum. You're seeing yourself reflected, and what's happening is electric charges are jostling back and forth in that aluminum and reflecting the light waves very efficiently. So electrical conductors are particularly good at reflecting electromagnetic waves, and that means that electrical conductors in this room will not show you their own thermal radiation. What they do instead is reflect the thermal radiation from things in front of them. So you'll see a reflection of something else. You won't see. So these little gadgets that I sent this around, this little temperature radiative thermometer. It looks at thermal radiation. If you look at all the organic things in this room, including people, you'll see their temperature because they are pretty much black objects radiating very efficiently. If you go and you look at something that's metallic, shiny metal, real metal, not imitation, you'll see not the object, but whatever's like yourself looking at it. You'll see, this thing will see a reflection of you in that surface, and that's the temperature that it will report. Okay, so metals, you can't use these kind of gadgets to measure the temperature of metals. You'll measure something unintended. There are a few other things, non-metals, that have the same behavior, that reflect room temperature thermal radiation very nicely. They include the chemicals or the materials that are used to make displays. All the computer monitors, your watches, your cell phones. In many cases, you're looking through an electrical conductor, because in order to light up all the little pixels and stuff, they need to be able to put to do electrical interactions with those pixels from both sides, the back and the front. And the front is what you look through. So you're looking through an electrical conductor. That electrical conductor has a weird behavior that it's transparent in the visible, but it's electrically conducting enough that if you go into the infrared, it would look metallic, shiny metal. So those kind of special conductors they're only able to conduct in certain regimes, and you can't see their reflectivity in the visible. They're reflective in the infrared. Those, well, first of all, they're useful for all these computer monitors and stuff, but they're also useful for trying to control the flow of heat. And when I talk about how modern windows work, the multi-pane windows, the current best generations of multi-pane windows have those special electrical conductors on one of the surfaces, one of the internal surfaces of a multi-pane window, on a surface you can't touch, because if you touch it and scratch it, you cause trouble. Those internal surfaces are protected, and you can put one of these mirrors on. Sometimes they're called heat mirrors because they reflect thermal radiation at near room temperature, and they make it so that the two window panes can't exchange thermal radiation very easily. One pane, the coated pane, is terrible at emitting thermal radiation at the other pane, and the other pane simply sees a reflection of itself in that heat mirror on the first pane. So that it just ruins the two panes' ability to exchange heat by thermal radiation. You can barely see it. Sometimes you get a hint that there's that shiny infrared coating on the inside. It plays with visible light a little teeny bit, and it looks a little colored, but otherwise it's mostly invisible. Okay, so the main point of this harangue here is that you know that in the infrared, things are radiating. Almost everything's just glowing as brightly as it's capable of doing in the infrared, showing you its temperature, because its radiation is dependent entirely on its temperature. Its color is essentially black, the only exceptions being these conducting surfaces. Okay? Any questions about thermal radiation, the exchange of thermal radiation, heat by way of thermal radiation? All right. So now to go on to water, steam, and ice. The purpose of this is to talk about the phases of matter, solid, liquid, and gas, which you've known about forever, but to give you an idea of how these, why you have one versus the other, how they can coexist, how one can turn into the other, and vice versa. And we'll focus on one of the most important chemicals of everyday life, which is water, and its three forms. So opening question here is, if you have a glass of ice water, you certainly sat down with a glass of ice water, whether you drink it or not, and it's got both water in it, liquid, and ice simultaneously, and served to you, set down on the place in front of you, and it's been sitting there for a few minutes. And now I want to ask you about the temperatures of the ice and the water in that glass. They're both present. Okay, we assume they haven't disappeared. Which one's colder than the other, or are they at the same temperature? So how many think that the ice is colder than the water? How about the water is colder than the ice? How about they're the same temperature? Okay, so the vast majority of voters is going for the same temperature. A handful going for the ice is colder than the water. They are actually at the same temperature. They are coexisting at exactly the same temperature. I mean, for all practical purposes, it's exactly the same temperature. Ice can exist at this temperature or below. Water can exist at this temperature and above, but at this temperature, it's a special temperature where they're coexisting. They can coexist indefinitely. If you put them there at that temperature, it's a special temperature you're used to. It's the melting temperature of ice or the freezing temperature of water. It's, if you know it by number, it's 32 Fahrenheit or 0 Celsius. There are fine adjustments depending on the circumstance, but that's basically a special temperature where those two chemical substances or phases of matter can coexist. And so that's part of the story is how and why do they coexist. So water has three forms. Ice is common at 32 Fahrenheit and below. Water is common at 32 Fahrenheit and above. Steam is common at high temperatures. Incidentally, steam is not the mist that you see over a tea kettle. It is the clear gas that comes out of the neck of the tea kettle before the mist appears. So steam is an invisible, true gas of form of water. The mist that you see, that's actually little tiny water droplets that form when the steam cools. So that's not actually the steam. The steam is invisible. It's a transparent, uncolored, transparent gas. So those are the three phases of water, and they can sometimes coexist. In fact, it's possible for all three of them to coexist, meaning they're all three of them stably sitting there doing nothing or seemingly nothing, and they can stay that way all day and beyond. That's what I mean by coexisting. So the first question is, how can water and ice coexist in a glass? So just to get started with this. And while I talk about this, I want to lead into having water and ice coexist. And to do that, I want to make the ice first. So yes, we've got ice here, but I'm going to skip that ice because it's boring and make ice the good way. Okay. And the reason for that is ice, like, it's not a totally typical solid, but solids, you can cool solids down and they get colder and colder. You can make them as cold as you like. And how cold I like, so I guess he's got I can zoom the video in here just for a second. So I'm going to cool the ice down. I don't even need that much, just a little. I'm going to cool it down with a temperature measuring gadget here. This is reading temperature there, 21 C. If I hold it in my fingers, it'll go up 23, 24, hot stuff, all right. So I'm going to put the temperature measuring device into the water, and then I am going to freeze the water with liquid nitrogen. And my goal is to trap the temperature measuring device in the ice that I'm creating. Snap, crackle, pop here. My fingers are starting to consider becoming ice themselves. This is getting quite cold. All right. I have trapped the, okay, so you can read the temperature, minus 15 C, this is in Celsius, minus 22, 27. It's getting cold fast. There's still a little liquid water left, but I'll get rid of all of it. The point of this is ice can be as cold as you like. You can drop it right down to absolute zero. We won't get quite there, but we're at minus 60 C. It's getting pretty cold. And you've all encountered ice that was that cold. When you go into a freezer and pull out the ice cubes, they're very cold. They are not anywhere near 32 Fahrenheit, 0 Celsius. They're maybe 0 Fahrenheit. They're cold enough that if your fingers are wet, they freeze the water on your fingers very fast, right? So you pick up, your fingers are wet, you reach in and grab the ice, and they stick to your fingers. Familiar phenomena? It's because you're grabbing very cold ice. If you go and somebody encourages you to lick the ice on a metal pole on a winter day, don't do it. It's very cold. Your tongue freezes there. Okay, so we're now at minus 100 C. So we've got really cold ice. Cold fingers too. I want to get this out without, okay, I'm not even going to try. I'm going to dump out the rest of the water here. Change of plan here. Smaller beaker. All right. I am going to let this melt. I'm going to, it is now warming up from minus 81, minus 79, minus 78. It's going to be warming up, and I will let it warm up for a while, and come back and talk about it in a minute. What to remember, we made ice very cold. It's now gradually warming up. Why? Because it's the coldest thing in the room other than the bucket of liquid nitrogen, which is at minus 300 Fahrenheit, minus 200 Celsius. It's pretty cold. So I'm going to let it warm up. And it's not going to warm up forever. It'll warm up to a specific temperature. It's going to warm up to 0 Celsius, which is equivalent to 32 Fahrenheit, and then something special is going to happen. So it's going to work its way up like it's a chunk of salt, and it's just going to warm up from really bitter cold to hotter and hotter and hotter and hotter until it gets to that special temperature, 0 Celsius, 32 Fahrenheit, at which point it's going to begin to melt. So it's not a grand surprise. You've seen all these things before. But when it starts to melt, the temperature will stop rising. Heat is flowing into it now and causing its temperature to increase. It's going from solid ice to warmer solid ice to still warmer solid ice and so on. When it gets to 32 Fahrenheit, I'll just stick with 1. The additional heat that goes in won't go into raising its temperature. It will go into melting the ice into water. And that's my hope that this demonstration will work out to do. It's now at minus 63 degrees Fahrenheit. It's going to take it a little while before it gets up to 0. It's at minus 62 Celsius. It'll take a little while before it gets to 0 Celsius. Okay, so you okay with what I've got started going here? All right, so with that, then I can have some time to talk. This demonstration is always hard to do because of the timing issues. These take time, and whatever way I do it, it's awkward. Anyway, ice is a solid, and you know solids have a fixed shape and fixed volume. So by fixed volume, I mean that ice, a kilogram of ice is going to occupy about 1 liter of volume no matter what you do to it. Squeeze it, smash it, do whatever you like. It's going to be about 1 liter of volume. It's basically incompressible. Solids are incompressible materials. Unlike gases are compressible, right? You can pack them twice as tightly, double their density. You can't change the density of ice for all practical purposes, even if you smush it hard. Ice also has a fixed shape. If the ice cube looks like a swan on the table there, it's going to look like a swan until it's gone. Water is a liquid. It's still incompressible. You still can't pack it tighter than it already is. So it's about a kilogram of water occupies about 1 liter of volume no matter what you do to it. But what you can do is change its shape. So water, obviously, liquid water, you can pour it into a bucket and it'll fill the buckets, trying to lower its total potential energy as much as possible. It'll go as far down into the bucket as it can. Okay? Steam, also called water vapor, is a gas. It's transparent, as I said. You don't see it at all. It's not the mist. It's a gas, and it has a variable shape and volume. You can pack the water molecules more tightly, less tightly. You can put them in a bucket that looks like whatever bucket you want, and it will basically fill the bucket as best it can. All right. Ice and water have a special temperature, and that's this 32 Fahrenheit. Below 32 Fahrenheit, solid ice is the stable phase. These phases of matter, there are various, the word phase shows up in science in a bunch of different contexts. So these are the phases of matter of the solid, liquid, gas. And at low temperatures, that is anything up to in 32 Fahrenheit, the stable phase is a solid. If you put liquid water into an environment that's colder than 32 Fahrenheit, it's going to come back in not too long, it's going to be all solid because the liquid phase is not stable there. It's the solid phase. Above 32 Fahrenheit, the liquid phase is the one that's stable. Ice is unstable. If you put ice in a world of 40 degrees Fahrenheit and you let it sit for a while, the ice is going to be all gone. It's going to be replaced entirely by liquid phase. It's at that special temperature in between 32 Fahrenheit where the two of them can coexist indefinitely. You can have 50% ice, 50% liquid water, and it can stay that way all day. So it's special. And part of the story here is telling you sort of why is that special? What about that temperature is happening that makes it special? So that's the background. And we're now at minus 43 Celsius for that chunk of ice. It's still, incidentally, all solid ice in here. There's no liquid water. If I try pouring, nothing pours out. It's a solid because it's in that regime below 32 Fahrenheit, 0 Celsius, where the ice is the stable phase. Liquid water, not so. All right, so why is 32 Fahrenheit special? Whenever you've got two phases of matter present simultaneously, so in this case, suppose that you do have liquid water and solid ice simultaneously present, regardless of whether the amount of ice is changing or the amount of water is changing, the interfaces between the two, the places where they touch, are busy. They're not static, motionless, nothing is happening there. So imagine your glass of ice water at the restaurant. The surface of the ice has water molecules right to its surface as part of the ice, and those water molecules periodically break free of the surface and leave as liquid water molecules. And at the same time, liquid water molecules, ones traveling around in the liquid phase, periodically land on the surface and stick and become ice. So there's a constant exchange of molecules across that interface between the two, ice and liquid water. I think of these as like a really busy airport with planes landing and leaving all the time. That's my go-to analogy. And so the ice, for example, in this case, could be on the ground. So there are airplanes on the ground, and there are also airplanes flying around in the sky. And when ice, that is liquid ice, which is the ground, and water, which is the air, when they're touching one another, there are water molecules, which are airplanes, taken off the ice and landing from the air. So leaving the ice for the liquid water and simultaneously leaving the liquid water for the ice, back and forth, based on statistics. So it's not as if the same water molecule takes off and lands. It might, but it's a perpetual exchange of molecules between the two materials, the two phases of matter. I'll leave the analogy alone for now. But can you visualize this? This is a container of ice. It's wet ice, meaning that there's water all over it, liquid water all over it. This, incidentally, has a temperature we all know. It's at 32 Fahrenheit or 0 Celsius. How do I know that? It's because the liquid water and the solid ice are coexisting. That's the only temperature they can. Right now, because that chunk of ice that I made with liquid nitrogen is so cold, it's still minus 30 Celsius. If there were a little bit of liquid water around, its water molecules would land on the ice more often than water molecules would break free of the ice to go into liquid. And the ice would grow and the liquid would shrink until there was no liquid left. And that's why, and I'll say it again more carefully, that's why at low temperatures, below 32 Fahrenheit, ice is the only stable phase. Why? It's because when suppose you did have liquid water and solid ice together at 0 Fahrenheit, really cold, as cold as Charlottesville gets. You have them both there, and you look at what's going on, the action at the interface. There will still be water molecules leaving the ice for the liquid water, and there will be water molecules leaving the water for the ice. But the statistics will be skewed. Why? They'll be skewed. In what way? The landing process of liquid water on the ice will be much faster than the leaving process of water molecules leaving the ice for the liquid. And why is that? I think that's the next. This is not exactly helpful yet. The reasons for that. The rate at which water molecules leave liquid water for the ice is just determined by the density of the water. How many water molecules there are per liter. Because they're just going to be rattling around and bumping. And the more they are per liter, the more often they're going to bump on the ice and consider landing. So the landing process depends almost entirely on just sheer density of the water molecules. The leaving process from the solid ice depends on the amount of thermal energy that's around. The more thermal energy is around in the ice, and really it's thermal energy per kilogram, the more likely it is that a water molecule will find the energy that it needs to break free of the ice. And at this point, I should point out that what distinguishes solid ice from liquid water, part of it is an energy. Turning solid ice into liquid water takes energy. Why? Because the particles in solid ice, the water molecules, have formed essentially chemical bonds with each other. They're not the official fancy chemical bonds that hold together, say, organic molecules that hold a protein together. But they are pretty strong. They're a chemical bond known as a hydrogen bond you may have encountered in chemistry. They're pretty strong. And they're not quite at the level of official chemical bonds, but they're strong enough that once the water molecules have been allowed to settle into their favorite organization as solid ice, that process releases a lot of chemical potential energy that has gone away. And to get them to free up and stop clinging as tightly as they are in solid ice takes some added energy, a lot of added energy actually. So melting ice into water takes a considerable amount of added energy. That added energy is known as the latent heat of, well, officially it's known as latent heat of fusion, where fusion is a fancy word for melting. So I just call it the latent heat of melting. It's the heat you have to add to solid ice to melt it into liquid water without even changing the temperature. It's just an addition of energy that's required to just break all those little chemical bonds that are holding the water molecules together as a solid. Is that okay? So returning to this issue of you've got solid ice and you've got liquid water and it's bitter cold. What's going on? The water molecules are landing from liquid water onto the solid ice perfectly happily. They don't care about temperature. Right? There's the surface to bump into. Oh, I bumped into it. Oh, I stuck. Okay. So the rate at which they land has to do with how often they have an opportunity to bump in the surface. The water molecules trying to leave the solid ice have a different issue. to leave the solid ice, they have to get some extra energy because they are bound in there chemically. And for them to break free, they have to hold out a hat and say, you guys, all you nearby molecules, could you give me a little extra energy? I need to break free. And in bitter cold, they don't get the money they need. They don't get the energy they need. They're stuck. They don't leave very often. Once in a blue moon, one of the water molecules will get the energy that it needs to break free and go out. But the exchange of water molecules between the liquid water and the ice and the liquid water is very uneven at low temperatures. The water molecules land on the ice and stick way more often than they break free of the ice and leave. And so the ice, the solid phase grows, the liquid phase shrinks until there's no liquid left. So that's life at very cold temperatures, like minus 12 Celsius, still too cold for liquid water. If I put a drop of liquid water in there, this exchange is going to go on until the liquid water is going to land. It's not going to get water molecules back from the solid. The liquid phase is going to shrink until it's all replaced with solid. Okay? Once we get to 32 Fahrenheit, or 0 Celsius on this scale, the landing leaving hit balance. That is, there's enough thermal energy around at 0 Celsius. There's enough thermal energy. Remember, temperature is measuring the average thermal kinetic energy per particle. Right there at 0 Celsius, there is enough thermal energy around to break water molecules free of the ice at exactly the same rate they land from liquid water on the ice. The two rates reach balance. And the solid ice can keep sending off water molecules and receiving back water molecules and not change the amount of ice there is. Same with the water. The water it's exchanging water molecules. If you painted them, hypothetically, if you painted the water molecules in the liquid blue and the water molecules in the ice red, you would see the colors drifting as this exchange occurs. But there would still be the same number of red molecules on ice molecules and the same number of water molecules. They would just be exchanging and making no progress. All right? Once you go above 0 Celsius into the land where, in the regime in which water is the only stable phase, the water molecules leave the ice too fast. They find the thermal energy they need to break free way too often. They parade out into the liquid water and are not replaced fast enough. So the ice melts away to nothing. And so above 32 Fahrenheit, 0 Celsius, you've got liquid water. Below 32 Fahrenheit, 0 Celsius, you've got solid ice. Right at 32, you can have both. And if you want to, so suppose you're there, right at that special in between temperature, and you've got half of the water molecules in your container are in the form of ice, and half of them are in liquid water. They will sit there all day as long as you do not add or remove heat. So that's what this view graph's about. Suppose you got a 50-50 mix of ice and water. If you add heat, that heat will go into the system and it will encourage the leaving of water molecules from the ice into the liquid water without a replacement. So the temperature of the material won't change. It'll still stay right there at that special melting temperature. However, the ice will shrink in favor of the liquid water, and then it will be stable. Assuming you added some heat and then you stopped. You'll just shift the balance between water and ice a little bit in favor of more liquid water. If you take heat out, you'll shift it the other way. You'll shift the balance in favor of more solid ice. But the temperature is very hard. The temperature is sort of self-regulating. It will sit right there at that special temperature, assuming you don't really add heat seriously fast or remove it seriously fast. You can take things a little bit out of steady state and sort of equilibrium if you're too aggressive. But for all practical purposes, the temperature of the water and ice mixture will just sit there at the same melting temperature while you shrink the ice and grow the water, or shrink the water and grow the ice, either way. We're now at -4 degrees Celsius. And I'm going to zoom back in on this guy. This is 2, right? Yeah. We're coming up on the point at which the system will start to have, for the first time, liquid water. And once liquid water is there, the additional heat flowing into this still quite cold object from the room will go not into increasing its temperature, but into melting the ice into liquid water. So the temperature should go to basically to 0 C, give or take a tiny bit, and just sit there. And while it's sitting there, the ice is melting into liquid water. And it will just sit there while the ice melts until there's no ice left, at which point the temperature will begin to rise again, because now you're just heating liquid water. And when you add heat to liquid water, you make hotter water. When you add heat to solid ice, you make hotter ice. When you add heat to a mixture of ice and water, you melt the ice into liquid water. That's where the heat goes. It doesn't go into raising the temperature. In fact, it goes into the heat of melting, what I call the heat of melting, latent heat of melting. We're at -2, so we're close. You okay with this transition story? Yeah, Anna? Okay, so Anna's question is about the density of the water around the ice. Water is almost a unique chemical in nature. It has, most chemicals in nature are at their densest when they are a solid. Chunk of iron, it's at its densest when it's solid iron. And when you begin to melt it, the liquid iron is a little less dense than solid iron, and it gets less and less and less dense as you heat that liquid hotter and hotter. So this is why solid iron, for example, sinks in liquid iron. And iron just came off the top of my head, but just pretty much pick any material like salt, melt sugar. Almost all solid, pick a chemical, the solid form of that chemical sinks in the liquid form of that chemical, because the solid form is more dense. Does that make sense? It's a buoyancy issue. Solids, if they're more dense than the liquid, you put them in there, they displace. They get a buoyant force, but not enough to support them. They go to the bottom. Water is almost unique in nature that when you melt ice into liquid water, it's more dense than the solid. Liquid water, right there at the melting temperature, is surprisingly dense, more dense than solid ice. Maybe it's more like solid ice is surprisingly low dense, undense. The crystallization process kind of fluffs it up. So liquid water is more dense than solid ice. What does that mean for ice in liquid water at the melting temperature? Does it float or sink? How many think that it floats? How many think it sinks? Yeah, it floats. This is why icebergs float. If it weren't for this, there would be no icebergs. The Titanic would still be going back and forth to Europe. So the fact that ice floats on its own liquid phase is almost unique in nature. And the fact that the liquid water is relatively dense compared to the ice surely affects the melting temperature. If the water were less dense than the ice, the landing process would be slower. And what would that do to the melting temperature? It would make it easier to, melting temperature would go, it's a multiple choice question on the test. What is it? The landing is now, it's harder for it to land. The landing rate's reduced. It's easier to match it. It would depress the melting temperature. Ice would melt instead of 32 Fahrenheit, it would be 30 Fahrenheit. This guy's at -4 and sitting there, incidentally. That idea, just to generalize this, as I'm here paralyzed trying to think of the answer, depressing the melting temperature, in this case, by making it harder for water molecules to land. This thought process, I mean, where was this coming from? If water weren't so remarkably dense once it melts, if it were just ordinary, the landing process would be weaker And so you'd have to go colder before you managed to make the ice stable. That happens when you do anything to water that makes it harder for the water molecules to land. What's anything? Add salt to it, add sugar to it, add anything that dissolves in it. You make it harder for the water molecules to land. They're busy looking after the salt molecules, for example, the particles in the salt. So the melting temperature of the ice and water mixture, instead of being 32 Fahrenheit, it's lower, maybe 20 Fahrenheit or 10. This is why you sprinkle salt on the roads or on your walkway if you want to try to make it harder for the ice to be there. You're making it more, you're upsetting the balance between the landing and leaving at the surface. You're making it harder for the water molecules to land, and therefore you're favoring the liquid phase. You're making it easier for the water molecules corresponding to leave the ice, and the ice shrinks. So anything you do that occupies the water molecule's attention depresses the melting temperature of ice. All right? This is having a terrible time changing temperature now. It's sitting here at minus 0.3 of a degree. It's going to sit there for the rest of class because at this point there is some liquid water in this. Can I show you that? That would be not really. It could be trapped deep inside the ice. We don't know where the liquid water is starting to show up. But that's going to have a terrible time getting hotter because all the thermal energy that's flowing into it, because it's cold, is going into melting the ice, not into raising the temperature. Is that okay? All right. So basically, melting and freezing ice. If you want to melt ice, add heat, and you've got a mixture of water and ice. You want to melt the ice in favor of the liquid water, add heat. That'll do it. There's a comment about pressure, and I'm not even going to talk about it. You can play with pressure to melt or freeze ice, but that's a long story. To freeze water into ice, take heat out of it. You'll convert the liquid water into solid water. You'll favor the building of the solid. All right? And just in general, the process of melting, from going from pure solid ice at the melting temperature to pure water at the melting temperature, no change in temperature, that transition takes a lot of energy. And that energy that you add in order to go from the solid to the liquid is the latent heat of melting. And it's a significant amount. This is useful to you because it means that solid ice takes a lot of heat to melt solid ice without even changing its temperature. So ice becomes a good refrigerant, in effect. If you've got stuff you want to keep your food cold, just bury it in ice. The food will transfer heat into the ice. The room will transfer heat into the ice. Until that ice is all liquid, all melted, it's going to keep absorbing heat. And just that heat won't raise its temperature. It will just turn it into liquid. Okay, so so far what I've done is two phase transitions. Phase transitions are just a general concept of converting one material phase into a second material phase. In this case, we have converted, conceptually at least, solid ice into liquid water, and liquid water into solid ice. It's two directions across the same phase transition. There are, however, two more pairs of phase transitions. Liquid water into gaseous water, and gaseous water into liquid water. That's one pair. You know them as evaporation and condensation, I hope. When liquid water turns into gaseous water, that's evaporation. When gaseous water turns into liquid water, that's condensation. The last pair of phase transitions is between the solid and the gas, which this is more exotic. You don't think of solids turning into gases, but they do, and vice versa. When a solid turns directly into a gas and skips the liquid, that's called sublimation. You're familiar with that when the ice cubes in your frost-free freezer just gradually disappear. Not the cheapo freezers that you guys get in your dorm room, but the fancy refrigerators that are frost-free. You probably have noticed that you go to the ice cubes have been sitting there for 6 months because nobody used them, and you open the door, and they're all like midget ice cubes. What happened to them? they lost water molecules directly to the gas, and that's sublimation. The opposite of sublimation, when the gaseous water turns directly into solid ice, that's called frost. Well, that creates frost. It's called deposition officially. The name, just think of it as frost. What is frost? You've seen frost appear on windshields and stuff like that, or on the grass on really cold days. That's gaseous water molecules landing on the surface and immediately building the solid. The physics at the interface between the two phases is the same as what I've just described. There's this landing-leaving process going on all the time. If I just put water on the table here, it's like we're at minus 0.2 degrees. Nothing's changing. We're just making liquid water. Do I have anything I can pour yet? Nope. It's just melting. So right now, there's landing and leaving going on here all the time. And water molecules are leaving the liquid water for the gaseous water. There is incidentally gaseous water, and you're breathing it right now. Several percent of the several percent of the molecules you are breathing with every breath are not nitrogen, not oxygen, not carbon dioxide. They are water molecules. So there are lots of water molecules here. We're looking through them. And they're leaving this liquid surface for the gas, and they're going from the gas to liquid surface back and forth, back and forth. And what matters to most of us the most is, well, is there any net transfer? The transfer is going on all the time. The question is, are they leaving the liquid water for the gas more often than the reverse? And if they are, the liquid water gradually shrinks. And as it shrinks, it evaporates. So evaporation occurs when the leaving process dominates. And that occurs typically at high temperature, because again, it takes energy to break those water molecules free and send them off on their merry way as a gas. So the hotter it is, the easier it is for those water molecules to take off and leave. On the other hand, if the water molecules, instead of there being a net leaving off that liquid water, there's a net landing of water molecules on that liquid water. That's condensation, and that occurs typically at lower temperatures when it's hard for the water molecules to break free from the liquid. So when they land, they don't take off again. And you've seen evaporation and condensation in a billion contexts. On a warm day where there's not much water in the air, and it would be described as dry air. We'll talk about that another day. When the air is dry and it's warm, the water evaporates nicely. The leaving process dominates. The water molecules break free of the liquid and become a gas, and the water just shrinks. And when it's cool, and there's a lot of water molecule in the air. For example, in a bathroom, when someone's taking a shower, and there's just gobs of water molecules in the air, and they encounter something cold like the mirror. They land on the mirror and stick, and then they can't leave because there's not enough thermal energy to break free. So they accumulate there as liquid water, and that's the process is known as condensation, but it's the same dynamic balance between landing and leaving. We'll see the same dynamic balance with sublimation and deposition, but that's down the road. What I also want to have to talk about is boiling. Boiling is not a special phase transition. It is an enhanced version of evaporation. So we're set up for it, but we'll do it on Wednesday. What day is today? All right, see you on Wednesday.